Hello, everyone, and welcome. We are, believe it or not, at Module 11 of Multivariate Statistics for this semester. And we are going to start in Module 11 talking about structural equation modeling. If you remember last module, Module 10, we talked about confirmatory factor analysis. We learned a little bit about what path models look like, and got a little bit into latent variable modeling. And now we're going to lean into that just a little bit more and learn quite a bit more about path analysis and the ways in which you can use structural equation modeling, which is an incredibly flexible method that affords so many options in terms of how you might want to look at data. So I have the R Markdown file up and ready to go. I also have a timer going here, so bear with me. I may split this into a couple of videos. There's a decent amount to cover, or we may just roll this all into one. And I've pointed my my software here to the location where my data set can be found for week 11 or module 11. So let's go ahead and load in some packages first. A nice part about SEM is that you typically just need to use the lavaan package. There are a few others. We'll use SEM plot as well. But lavaan is kind of your workhorse here. We learned about lavaan last week when we talked about CFA, and then of course tidyverse. And then we're going to load in the data for this week, which is this same data set that we used when we studied logistic regression. So the file name here is lslogistic.dta. And we'll go ahead and get a look at this. So this is the exact same data set. And you'll notice lots of kind of strangely named variables. Just a refresher here. So these data come from the Educational Longitudinal Study of 2002, ELS. So this is a large secondary data set. This is a set of 55 variables taken from the bigger data set, which actually has thousands of variables. And we are going to use this to learn a little bit more about how to use SEM. So we're going to do a little bit of cleaning and coding here. And the first part of this, so again, I always recommend that you create, first you load in your original data set, and then you create a clean version of that data set, which is the one that you actually do your analysis on. I always like to leave that original data set relatively untouched once I've imported it into R. And the nice part about R, of course, is that you can do that. You can have multiple copies of the same data set open at the same time, and it's not a problem as long as you keep yourself straight as to which data set is which. So we're going to make a clean version of this data set, and it's going to be called els.clean. And we're going to start with the original els, and then there's our good old pipe operator. The first thing I'm going to do is address all these missing variable codes that are very common in secondary data sets. So if you notice, we have -9s, -8s, -7s, -4s, and -1s. We can even see some of those as we're looking at the raw data we've loaded in, right? So look at this string, for example, of -3s, right? And here's some -1s and -9s. So, oh, actually, there are some -3s. That's interesting. There must not be any -3s in our in the variables we're actually using. That's really interesting. So what you can do is identify. So this takes a little bit of digging. So you have to look at the code book for your data set. It's really important to look at the code book and find those individual variables that you want to use, and then identify what the missing data codes are. And then you can use this function called NAIF, and it will convert those missing values to missing, or NA in R. So you're going to lose that information, right? You're going to lose the difference between a legitimate skip and a survey non-response. But again, we can't really do much with those responses anyway. And so our best bet usually is to treat them as missing in the type of analysis like this. So that's the first half of this, is I'm just recoding those missing values. And remember, I saw some -3s up here. So if I pick a variable that has -3s, I could just add another line here and recode -3s as well. And then after that, we're going to use a cool function called transmute. Transmute, it's kind of a combination of the mutate function and the select function. So what it does is it performs the operations that mutate would perform. And we've used mutate a lot. So mutate is basically how you create a new variable based on some function of an existing variable. But what transmute does is it gets rid of all the other variables that aren't mentioned. So if you mention the variable here in this statement, it will stay in the new data set. And if you don't mention it, then it will be excluded. So this is nice for a large secondary data set, although this one isn't too big, it's only 50 variables. But if you had like 1,000 variables, for example, you could very quickly whittle down from your 1,000 variables into a smaller set of variables that you actually want to work with. And that's what I'm doing here using the transmute function. If I just did mutate, it would just tack those new variables on and all the other old variables would come with it. But here I'm just creating a new slimmer data set that I'm actually going to work with. And all I'm going to do is make copies of my variables, but then give them names that make more sense to me. So here's this variable BYS43. This is how many hours you read at home or read at home in the past week. The variable BYS87A is actually to what extent do you get absorbed in math while working in math class. Same thing for reading. Math importance is measured by BYS87F. Comp test is a composite achievement kind of test. We have a factor here, variable for sex, and I'm using the as factor converter here. And this is a variable that measures SES in quartile. And again, I'm converting that to a factor. So that will accomplish most of my data cleaning and coding. So I use transmute. And now if I look up here, my new data set only has 7 variables. And here they are, 1, 2, 3, 4, 5, 6, 7. So that's really handy, a nice trick. Okay, so given that, I can now sort of get a better sense of how everything works with path analysis. So the first thing we're going to do with path analysis, and I try to explain this, if you haven't watched a lecture, I recommend that you do so. Path analysis is like a whole different framework for doing statistics. It is not one method. It is a framework. It is a way of understanding relationships between variables and estimating the relationships the variables have with each other. So in this way, and remember I used that example of the rug, right? I love that movie, The Big Lebowski. So the rug is the thing that ties the room together. So path analysis and SEM kind of are that kind of method that ties all these other statistical techniques that we have learned together in one sort of modeling framework, which is really cool. So the first thing I'm going to show you how to do is basically like a regression, a simple linear regression or a correlation. So we're going to start simple here, and we're going to try to replicate as many of these methods as we can. So the first one we're going to start with, again, is simple linear regression or correlation. So the first thing you do when you specify a model, and notice I made a comment here about missing data, and I'll get to that in a minute. And you're probably seeing that on your handout and wondering about that. So what you do in an SEM model, we learned about this last week when we learned about CFA, is you have to specify the model first in text, and then you fit the model in lavaan. And so the approach is exactly the same. So if we want to fit a simple linear regression, the command actually looks very similar to how we would write out a linear model, but we give it a name, model 1. And again, everything goes in single quotation marks. So you'll notice it turns a different color. And the model we're going to look at now is, what is the correlation between composite achievement, just a general measure of achievement, and how absorbed you are in your reading class or your English class. So you can think of that as like a measure of engagement, basically, like cognitive engagement. You know, if you get really absorbed in class, you're probably pretty cognitively engaged. I know my ed psych people are saying that's probably not a perfect measure, and you're absolutely right, but it's enough to get us started. So here's a relationship here. So I've specified it. So now it's up here under values. And to fit this model, I just create another object, and I'm going to call this fit1 to match model one. And that is going to be an SEM, because we're now doing SEM and not CFA. So SEM of model one. Our data are ELS clean, and our estimator here, I'll get to in 1 second. Now the format is the outcome is listed first, just like in a linear model, and then the tilde is introduced. So that's usually means regressed on. So the outcome regressed on the predictor. So the composite test is our outcome, and it is regressed on the predictor, which is absorbed in reading. Now, this is a simple linear regression. It's also a correlation if you get the standardized estimates of this. So by standardizing the estimates, the standardized regression coefficient in simple linear regression, not multiple linear regression where you have other predictors, then it's a partial correlation. So we can't do that. But in simple linear regression, the standardized regression coefficient is a correlation. So this actually will give you a correlation. And then we can fit this model as follows. So we're going to run this. And then once the model has been fit, notice I now have a new thing called fit1 up here. I can just say summary fit1 standardized equals true. And this is the same approach that we use during CFA. You specify a model in text, you fit the model, and then you get a summary of that model. The output looks pretty similar. What's interesting though, so here the estimator here is MLR. And what's pretty cool is that we essentially are using handling our missing data, which is really cool. So this column, notice it says used, and it says 11,603. So that means there were, out of a total of 16,000 people, we had 5,000 people who were missing either a composite test score or a reading score, okay? But using the robust model, which is right here, which is where we got our information, we actually were able to use all 16,197 observations. So using this trick, I call it a trick, but it's really cool. So this is called full information maximum likelihood. So what happens is if anyone has provided even one of those scores, so even if somebody has done has answered absorb read, but they haven't answered or they don't have a score for the composite test, or vice versa, if they have a score for the test but not for the other, those people are still going to be included because full information maximum likelihood can handle incomplete data. It accounts for missing data. So this is actually very similar to the results you'd get using multiple imputation. So way easier, right? You're not having to specify a multiple imputation model. And wow, does that make path modeling, path analysis, and SEM really cool. It's a real advantage to be able to do that. So anyway, let's get into the results here. Notice we don't get any fit statistics. Our test statistic, our chi-square is 0, and we have 0 degrees of freedom. The reason why is that we have what's called a just identified model. So we don't have anything latent in this situation. We're not estimating a latent variable. And because we're estimating the relationship between two observed variables, all the information is accounted for. So our data points and the number of parameters we want to estimate are the same. And so we don't have any degrees of freedom to assess model fit, which is totally fine. In this case, we're not so worried about a latent variable, and so that's absolutely fine. So our results are here where it says regressions. So here is the regression for comp test as the outcome and absorbed with reading as the predictor. And here again, we get an unstandardized estimate, a standard error, a p-value, and a test statistic. So those two are significantly related to one another with a very low p-value. But then if we look over here, this last column, this is just like in CFA, is the standardized estimate. And this is equivalent to the correlation between composite tests and absorbed in reading, and it's 0.23. So interestingly, there's actually a negative relationship here between this composite achievement test, whatever it is, and being absorbed in reading. A little bit different than you might expect. So we have a negative relationship. So you can do this for any two continuous variables. You can use the same setup and you can obtain either a correlation or a simple linear regression coefficient, which is pretty cool. We can also visualize this. Again, this is the same command we used last week. So SEM plot is the package, and then SEM paths is the function. And then you just put the name of the fit in there. So fit one, the name of the model. And then I'm going to ask for standardized labels. So here, as we can see, absorb and reading, that's my predictor. This is my outcome down here, which is our composite achievement. And this arrow is pointing from absorbed in reading to our outcome. So that's actually the model we just fit, a little tiny regression. Here is the coefficient, minus 0.23. The variance of this thing is fixed at 1, mean 0. And this is the residual variance, the error variance. And this is the estimate of the error variance for our composite score, which is actually not something we usually get in regression, but that's provided there too. But what we're really interested here is the coefficient and the size of that coefficient. So that's the correlation between the two. And that's a visual way to represent the relationship between the two. Okay, we can actually replicate this using a regression setup and the LM function, which we learned about back when we studied regression. So model 2 is a regression model, and it is a linear model with achievement as the outcome, and absorbed in reading is the predictor, and our data is ELS clean. And then we get the summary. And notice we get the same coefficient, minus 2.37. That's the effect or the relationship between absorbed in reading and composite achievement. And we get a pretty low p-value. And if we scroll up here to our results, look at that, minus 2.37. So in SEM, we've effectively replicated a regression model. And that's the cool, flexible part about SEM. It's not just about latent variables. It's a framework for fitting a whole bunch of different statistical models. And so this is just to show you, you get essentially the same results. Here we're using what's called ordinary least squares estimation. SEM by default uses maximum likelihood estimation, but otherwise it's exactly the same. And in SEM, we're actually handling all 16,000 observations, whereas in regression, right, we still have that limitation of list-wise deletion. And so we're only handling about 11,000 observations. So pretty cool. Okay, so that is essentially a correlation or a regression in a path analytic framework. And you could add predictors here if you wanted, just with a plus sign. So absorb read plus absorb math plus something else if you wanted to run a more extensive regression, which we'll get to in a little bit later. All right, so I want to talk about t-tests, and then I will take a little break because I'm noticing my timer here. I want to keep this pretty short. So the next thing I'm going to show you how to run is an independent samples t-test in a path analysis framework. So let's say we want to know if engagement in math differs according to the student's reported sex. So in this case, sex is only represented here in two categories, male and female. Keep in mind the data here come from 2002. Since then, we have gotten much better at collecting more inclusive measures of gender and sexual identity. And so this would be flexible to multiple categories, right? Which is what we're going to do when we get to ANOVA below. But for now, we're just going to look at this comparison to see if there is a difference. And so first of all, we can, what I recommend doing is doing a table command for this variable sex to see what the values are, since it's a categorical variable. And notice We had some survey legitimate skips and non-respondents, but those all have been coded to missing. And then we have about 7,600 male and 7,700 female respondents. So those are the two categories. Now, here's the tricky part. lavaan and path analysis in general cannot handle categorical variables as factors. They cannot be factors. And so what you have to do is you have to take your factors and you have to convert them into dummy variables. So this is one extra step that can be kind of a pain, especially when you have a categorical variable that has a lot of levels. But it's not too hard, and this is a trick of how to do this. So we've actually done this before, something similar. So we're going to use this function called case when to create a dummy variable to represent when the respondent is male versus female. And so what I'm going to do is I'm going to take my new data set and I'm going to start with it, and then I'm going to mutate, and I'm going to create a new variable called male, and that is equal to a case when sex is equal to male, and I just got that right here from the label. I want this new variable to equal 1. And when sex is equal to female, I want this new variable to equal 0. So I'm going to run this like that. And we can even do, so I'm going to open this up and just do a glimpse to show you. You can double check that this thing actually worked. So glimpse els.clean. So here's our new data set. So here is the original variable sex, which is a factor. So the first observation, the person reported being female, that should be a 0 for my variable males. It is. And so the first 1, 2, 3, 4, 5 responses should be female. 1, 2, 3, 4, 5. The 6th should be male. And there it is. So you can just kind of spot check that a little bit. So now that we have a dummy variable, we can actually specify a t-test, an independent samples t-test in a path analysis framework, because a t-test is just a regression with a continuous outcome and a single categorical variable, a dummy variable, as a predictor. That's all it is. It's a comparison between two groups. And in regression, that's the simplest way to compare two groups, is to create a dummy variable and make that the only predictor of your outcome. So here it is. This is model 3. And we're looking at absorbed math. So math engagement is our outcome. Male is our predictor. It's a dummy variable, right? And then we're going to fit this thing using the SEM command. Here are the data, and we're using this fancy MLR estimator to handle missing data. And then we're going to get a summary of this. And I always do standardized estimates just because I really like them. Again, this is a just identified model. We're not estimating anything latent. We don't have any extra degrees of freedom. Here is the estimate, and it is minus 0.08, or I guess we should look at standardized, minus 0.05, and it is statistically significant. So male is the estimated group. Our reference group is female. So that means that males actually have a slightly lower level of math engagement compared to females. Pretty small though, minus 0.05. So not a big difference. But in a data set of this size, even a difference of that small a magnitude is statistically significant. So this is essentially a t-test. So if you ran a t-test on the data, you would get roughly the same result, except again, we're handling missing data really nicely, and it's all sort of set up in a regression framework. We can get a picture of this thing with a path diagram. So here's our predictor male, pointing with our regression arrow towards math being absorbed in math. And here is the size of the effect, which is minus 0.05. So that is an independent samples t-test. All right, so this is probably a good place to stop, about 25 minutes in. So just to recap what we talked about, we first of all loaded in our secondary data, we recoded our missing values, and then we just started walking through in path analysis how to recreate many of the models that we've learned about before. So first we talked about a simple linear regression or a correlation. And then we compared that with a regular regression using the linear model function. And then we talked about an independent samples t-test. Remember, of course, in a path analysis framework, you have to create those dummy variables first. You can't use factors like you can in regression. And coming up next, we'll talk about ANOVAs. And then we'll start to talk about SEM and models when we start to combine CFA models and regression models into one cool combination. So that's all for now. I'll have much more soon.